Welcome to the Soil Movement and Slope Stability webinar. I'm Zina Farouk. As Simon mentioned, I'm the application engineer for Oasys. So if you've got any geotechnical technical questions, it'll be very good to direct them to me. And I am a geotechnical engineering background as well. I've designed a lot of different projects, including those involving slope stability, settlement analysis, and GSA raft or raft analysis. So that's a little bit of background on who's presenting today, but in terms of what we want to achieve today, we're going to be covering quite a lot in a short period of time, so you'll have to forgive me if I'm rushing through it all. But the objectives of the webinar today are to apply the analysis theory to produce designs, and that applies to slope, Pdisp, Xdisp, and GSA Raft, and also to present the analysis results for use in reports. Now, I might not directly show you how to do this, but I will show you how it's done through case studies and what's been done for reports and the like. So let's move on and start with slope stability analysis. For geotechnical slope stability analysis, our program is Oasys Slope. Oasys Slope carries out a limit equilibrium analysis of circular and non-circular slip surfaces. And it's also able to analyze reinforcing elements such as rock bolts, saw nails, and ground anchors. And this is according to British standards, for example. Slope analysis methods. There are 3 slope analysis methods that are covered in Oasys Slope. That's the Swedish circles method. But of more interest to most people would be the Bishop's method, which looks at horizontal interstice forces, and the Janbu method, which also looks at horizontal interstice forces. But it can deal with different types of problems. So it really depends on the type of engineering analysis as to what you would use. The inputs to slope are quite simple, and what I'll do is I'll show you the program itself. But you put the ground section in by layers, and so you input the layers of material. You input the strengths of the material. You can linearly vary cohesion with depth if that's required. You can put your groundwater profile in, reinforcement, the external forces, and the slip surface. So what I mean by the slip surface here is the slip definition. So are you interested in a single slope stability failure, for example? Are you looking at a grid and looking for the worst case? Is your slip surface going through a common point, or are you just interested in a defined radii? So that's really the slip surface definition is really dependent on the kind of problem you're looking at and what kind of output you're interested in. In terms of the outputs in slope, you get the graphical output, which is very helpful for reports. But you also get detailed information about each slip circle. So as you can see, you've got the X and Y coordinates here, the radius, the slip weight, the factor of safety, disturbing moment, and restoring moment. And for the tabular outputs, which can be exported into Excel, you also have the worst case information about the worst case slip surface, and that will give you the lowest factor of safety. So I'm just going to run through a case study very quickly. This is a very recent project. In fact, it's still being built. It's being done by Arup, and it's been done in Canada. It's the A30 or Autoroute 30 in Montreal. So you can see there's an image here of the construction. It's a 42-kilometer long 4-lane highway. It was commenced in spring 2009 and is scheduled to finish mid to late 2012. The engineers use the Oasys slope analysis, and this was done for the embankment design and for the cutting design, but I'll focus on the embankment design. The soil was divided into zones with various shear strength characteristics. A number of failure surfaces were checked, and due to the brittle nature of the clay underlying the surface stratigraphy, the minimum factor of safety was chosen to be 1.4. So really, it's got a much higher factor of safety because of brittle failure. So what I'll do is I'll just go into the file and show you the slope stability analysis file. And just show you how slope works really in the interface for slope. So what you start off with slope is the general parameters. So what kind of slip surface are you interested in, a circular or non-circular, the direction of slip, and so on and so forth. forth. As I covered very briefly, the analysis options, so Swedish bishops or Janbu, what kind of factor of safety you're looking for. The method of partial factors is in here, and what this does is it automatically, it allows you to input partial factors in there if you wanted, or it has automatic information in there for example, for BS 8006 and EC7 as well. So as you can see, it's got quite a lot in there. It's got design approach 1 and combinations 1 and 2 in there as well. So that helps quite a lot. And that's covered in another webinar as well, so I'll give you information about that near the end of this section. The material information is inputted, drained or undrained, and you've got the strength parameters in there as well. You can change the color of the material for your outputs. You've got a groundwater profile, you can put piezometers in there. The strata information is inputted in terms of coordinates, and often we use, for example, CAD plot to plot the coordinates and then put that in here. But Oasys is actually working on a direct DXF input. We've got slip surfaces as well, so as I mentioned, you can either choose a single point for your circle center, or you can choose a grid, and that would choose the worst case factor of safety. And you've got surface load, so you can put loads in there, and reinforcement. So this particular problem, as is taken from a case study, doesn't use reinforcement. But as you can see, we've got quite a number of options for reinforcement here, and that's particularly helpful. So without much further ado, we'll go into the graphical output. So as you can see here, it's chosen, what the analysis has done is it's used this grid, and it's extended the grid to whichever direction it needs to go into to choose the worst case factor of safety. So this is hitting 1.4. So as you can see, this embankment is successful in terms of the design parameters. Of interest to people is that you can actually plot a range of circles here, so you can see where your slip circles are going, and where the range of failures are occurring. So that gives you an idea of the problem, and you can also input labels very easily now. So, for example, if I say I wanted to label this particular slip surface, I go to OK, and I put a label in there. There you go. As you can see, it's got the slip surface information there, and you can put an arrow in there as well. So you've got the center, the radius, and the factor of safety in there as well. So that briefly covers what slope can do, and how the processes work in terms of inputs, outputs, and helping you with outputs for your reports. And this is a extract of the actual report. So this shows the kind of output that was used in the report for presentation purposes as well. So it's got the groundwater in here. As you can see, these labels are all from slope now, and that can all be inputted. And we've got the grid in here, and it's chosen, as you can see, this is a center point of the failure, and this is the actual failure. So in terms of what's coming in slope, there are developments which we're working on, and which should come over the upcoming year. One of them is the DXF imports. I briefly mentioned that. The British standards as well, so BS 8006, so the most recent reinforcement information according to BS 8006 will be in there. Analysis of pore pressures, we're working, the developers are working on better analysis of pore pressures, and that'll be available. And also the ability to put reinforcement into non-circular slip surfaces will also be available very soon. So, seeing that I covered slope so quickly, I would like to show you how to help yourself really with slope. And the Oasys software webpage is quite helpful. If you go to the slope product webpage, to your right-hand side, you'll see the support box and related webinars box. And this related webinars box will give you, for example, old webinars. But the support box will help you because it'll point you towards the tutorials, and the tutorials will give you a much more detailed overview of the program, and for example how to input reinforcement data, modeling non-circular slips, and so on and so forth. And as I said, the related webinars is covered within the product page, but if if you're also interested in watching other videos, be it webinars or tutorials or learning about the program, you can watch our YouTube. You could go onto our YouTube webpage, and a link to that is available at the bottom of every single one of the Oasys pages. So if you look at the bottom, you'll see all these small links here, and I suggest you go to a YouTube page and just have a look. So that's covered Oasys slope and slope stability failure. Now I'm going onto soil displacement for geotechnical design. We'll start off with Xdisp, which is the soil displacements due to excavations. So what I'm going to do with Xdisp is explain the analysis methodology first, and then go on to case studies and recent developments in Xdisp. We're due to release by the end of March Xdisp 19.3. So I'll introduce that to you and show you the changes that have come into Xdisp. But to start with, Xdisp calculates ground movements due to excavations. And the type of excavations it covers are, for example, tunnel excavations, shafts, retained cuts, and mined excavations. So I'll start with the analysis methodology for tunnel excavations. And the equations for the curves are generated from normal or Gaussian distributions. So it's basically an empirical relationship we're looking at. The normal distribution relationship shows a close match to tunneling-induced case study movements at ground and subsurface levels. So it's a very different type of analysis method, for example, to FE. And it can actually be difficult to achieve similar results using FE. So a recent paper by Adam Brooks and Potts shows a specific study of St. James's Park and looks at results afterwards and compares FE analysis, for example, to empirical design and shows the accuracy of empirical design in this case. And it's also described in Syria 2001. So in Xdisp, you just need the main parameters of importance really are volume loss and trop width parameter. So it's not analytically based, and on that basis, you don't need the soil properties such as strength and stiffness and so on and so forth. So from these two parameters, which is volume loss and trough width parameter, you get the complete three-dimensional behavior of the ground. So it's a very powerful tool, really, just based on two very simple parameters. So that covers tunneling and very briefly how tunneling analysis works. Mined excavations can also be covered, and Xdisp gives surface displacements due to mined excavations. And this is based on a paper and a method proposed by Wren et al. So if you're interested in this can be covered in more detail in the manual. Embedded wall excavations are very useful. A lot of the time in Xdisp, for example, if you're building a station and then you're building a tunnel, embedded wall excavations are particularly useful. And this has been done on a lot of major projects. So within Xdisp, we have surface displacement curves from Series C580, but you can actually input your own surface displacement curves. And what the surface displacement curve is that once you have an excavation, so once you maybe do some kind of cutting or retained wall, away from the surface, you'll have a displacement both at the surface and coming down towards the base of your excavation. So that's modeled by this particular graph here, for example. And so Xdisp would take this excavation, maybe excavations in different points, and information about your tunnel, and accumulate the displacements for you in 3D. And as well as giving the surface displacement and displacements due to excavations, Xdisp now carries out building damage assessments. And so the building damage assessments basically look at where the position of your building is. And what it does is it looks at the surface displacements and the surface strains, and it looks at how those strains affect your building and what damage category your building is in according to Berland. So this table here just gives, for example, information about the damage categories, which is available again in the manual, and the strains and the crack widths that cause the particular damage categories. But Xdisp calculates this all for you. So I briefly covered the analysis, and the inputs for Xdisp will give you an idea of how the program works. So you need to say the type of problem that you're going to analyze, whether it's a mine or tunneling and excavation. Displacement points, lines, or grids. And what this does is it says that, for example, you're interested in looking at the displacements along a specific grid. Or maybe, for example, you want the displacements along the crown of a tunnel, so you can put a displacement line in. Or maybe you're just interested in a particular point, so you put a displacement point in. Also information, obviously, about the tunnels or the walls and excavations and the buildings and the mines themselves. And from that, you get the outputs. So you get the actual displacements themselves and the building damage assessments. So these images here give you an idea of what's happening. So as you can see, you've got here some tunnels and you've got some excavations. And you've chosen, for this particular model, a grid has been chosen. So you can see the displacements along a grid. You can also see that there are some buildings here. So the building damage assessments could be done for each specific building. You can choose a line and plot lines, plot displacements along those lines, both vertical and horizontal in the X and Y. And also it produces building damage interaction charts for each specific building. So this little star here, if you can see it right at the bottom of your screen, will actually show you where your building fits in terms of different categories of damage. So now I'll just cover Xdisp 19.3 and the features that have been introduced. It's quite a significant update to Xdisp 19.2, and it's due at the end of March. In terms of analysis, new analysis features are available. So I think I've previously covered what Xdisp 19.2 could do. So it could say, for example, if you put a specific building in. Say your building is here within a plane. So this is a 2D plane we're looking at, and you've got a building. So we're just looking down onto the surface of the ground. This is where your building is, and you could specify the building damage. You could do a building damage assessment for it. However, maybe you're just interested in an area. So maybe you just want to know. Maybe you want to position your building, or you know that buildings are going to go in this area, or you just want to know your worst case areas. So where are the worst case strains? Are they here? Are they in this corner here? Where are they for a specific area? So now you can carry out a generic building damage assessment to do that. And the way you do it is you plot a polyline. So you plot a line along the center of that area. And what Xdisp does is it basically models a number of buildings along that line. So you don't need to give detailed information about the building as such. For example, the building properties and everything are not as important. But what it will do is it will input some generic buildings along that line, and it will look at the worst case, for example, strain along those particular points. So so along this line here, for example, the worst case strain might be here. But what Xdisp would do is it would plot it at this point here. And so what you would do is for this particular area, along this line, you can find out the worst case strains, and then you would know your worst case area. And you can assess, for example, you can assess whether there are buildings there or not. You can assess whether you can position buildings there or not. Of great importance and great use now is the specific and generic utility damage assessment. So I actually have to show you that. I think it would help if I did particularly show you how the utility damage assessment works. So as you can see here, there's you can put information about your utility in, and you can either have specific utilities or generic utilities. But what happens is in plan, I can show my utilities. I've just done a generic utility damage assessment here, which works along the same principles as a generic building damage assessment. And I can plot the properties for the utility as such. So you can choose, for example, displacement versus chainage. Where's the worst case displacement along that polyline? Where's the worst case rotation along that polyline? Pull out or combine strain. So if I look at rotation, you can see the maximum rotation is here and a rotation limit is here. And you could also see that here's the rotation along that polyline. So the worst case rotation for my utility is along the middle area. So that's a change along the polyline, and it's well within the rotation limit. But if I look at the worst case rotation, if I look at the problem and plan, it's where you would expect it to be. So it's along the center here of the polyline. So that gives you an idea very briefly of some of the updates in terms of analysis that are available in Xdisp 19.3. And I think utility damage assessment is particularly useful. It gives you new options, and it's quite good for a very densely populated area, for example. Inputs and outputs have also been worked on, as well as analysis. So we've got the graphical input, editing and deletion of model data via the 3D graphics view. So you can now put most of your inputs through the graphics view. And also you can import background data from DXF files for display in the 3D graphics view. And so that's very good for reports, for example, and it gives you a good pointer as to where your buildings are, and just checking your inputs and your outputs. So what I'm going to do for Xdisp is I'm going to cover a case study. This case study is very interesting, actually. It's the Copenhagen Metro. It was recently presented at the Tunneling 2020 conference, and it was designed by Arup and Covey. But this particular section was designed by Arup, and the geotechnical constraints for this construction was significant in terms of the fact that the design and construction of tunnels were in soft ground, and also there was a requirement to limit settlements, because a lot of the buildings in Copenhagen are on these wooden piles, and they can really be affected by settlements. So for that reason, Xdisp was particularly important. So the way Xdisp was used, that for any buildings where predicted settlement is more than 5 millimeters, or the slope is more than 1 in 500 millimeters, a building damage assessment is carried out. So if you look at this 3D image here, you can see that you've got these buildings here. So each of these buildings was assessed. And for the building damage assessment, as you can see, we've got our result within different damage categories. And as you can see, for this particular building, its maximum strain is well within the category 0, so it's obviously not of a worry. This red line here is category 3. You can also calculate predicted settlements along the structure, and that will help you look at the slope. So to finish off with Xdisp, again, I've covered a lot very quickly. So tutorials are available again on the website. For Xdisp in particular, you've got the introduction to 3D graphics, and you've got information about building damage assessments. So those tutorials will help you get your head around how building damage assessments works in 3D graphics. And with Xdisp 19.3 being released, new tutorials will be available as well. We've also got previous webinars which particularly pertain to Xdisp. So the introduction to Xdisp is there, and also Xdisp used in retaining wall analysis. And there are YouTube videos as well. So that moves me nicely on to Pdisp, which is soil displacement due to pressure. So we've covered displacement due to excavation, and now we're looking at displacement due to pressure. And Pdisp analyzes displacements due to the application of a pressure, and that's either a loading or an unloading pressure. So it can be used for, say, for example, an excavation or a demolition. So the typical use of Pdisp would be predicting ground settlement due to surcharging, ground settlement of a flexible footing or raft, and this fits in very well with GSA Raft, which we'll come to, and predicting settlement of tunnels, for example, due to loading or unloading of soil. So Pdisp is used extensively, for example, in the UK, in areas like London, where LUL tunnel movements are very important, and assessments need to be made. Pdisp analysis methods. There are two main analysis methods that you should be aware of. Details are given in the manual, but I'm going to cover it briefly here. And I think it's very important that you understand which analysis method to go for before you start your design. There's a Boussinesq method, which gives the stresses and displacements in the soil. And there's a Mindlin method, which gives the displacements only, but can also deal with shear. And this graph helps you really figure out which you should be going for. So, for example, if horizontal displacements and traction forces are important for your problem, or if you need a theoretically exact answer for some kind of homogeneous soil, you would be thinking about going for the Mindlin method. Whereas for the Boussinesq method, soil nonlinearity and stress changes are calculated. So if that's more important for your design, you can go for the Boussinesq. But actually, when you carry out the analysis in Pdisp, one useful feature is that it gives you a comparison of the two analyses. So it'll say at a specific point, at the worst case difference between the Mindlin and Boussinesq analysis is X number of millimeters, and that can be quite a helpful thing. So again, to understand how to use Pdisp, we have to understand the inputs. Again, like Xdisp and slope, the inputs are via gateway, but you can input grid lines and points for displacement. So this is very similar to Xdisp. So are you interested in a grid for displacement? Are you interested in a line? Maybe, for example, again, the crown of a tunnel or a specific point. Pdisp can plot that for you. It can give you that information in Excel for you to plot for yourself. So however you want to represent it, you can. The loaded areas are rectangles and circles. And the base is defined by a rigid boundary. And so when we say the base is defined by a rigid boundary, this might be rock, for example. So if your rock is 20 meters below ground level, then that might be where your rigid boundary is. The ground is modeled with vertical soil profiles and plans of soil zones. So it's shown here in a little bit of detail. So you can see for different soil profiles, you've got zones 1, zones 2, zones 3, and zones 4. But this is quite useful, for example, if you have a soil lens or if you have sloping ground. And the actual analysis methodology, so you're going from Mindlin or Boussinesq. So Pdisp is an elastic analysis. It's different to consolidation analysis. So the really important thing, for example, are the Poisson's ratios and the Young's modulus of the soil. So as you can see, you've got an example here showing the soil profiles and how they work with the different soil zones. In terms of loading, as you can see, you've got your rectangular loading here and circular loading. And the loading doesn't have to be horizontal, it can be tangential. So that's shown in this diagram here. The outputs of Pdisp have been worked on extensively. This is because it's particularly useful for reports and it's particularly attractive in reports. So you could have a contour for a specific grid. So say, for example, if this is the surface, the ground surface, you could have a contour indicating the worst case area for displacement. You could choose a displacement column, and what this does is, say, for example, for displacement at the point 0, 0, it will give you displacements and where it goes down to 0. So it gives you an idea of how displacements work for different parts of the stratigraphy. Or you could just have a 3D image and just show the displacements actually in terms of some kind of grid. So as you can see here, the displacements are showing very nicely, and you can see how it displaces in terms of the actual loadings. One thing I should mention also about Pdisp is that the tabular outputs, and this applies to Xdisp and slope, all the tabular outputs can be transferred into Excel. So if you want to do further analysis or present it in a slightly different way, you have the option to do that. So what I'm going to do with Pdisp is I'm going to go into a case study. The case study here is a comparison analysis to check LSDyna outputs. And the reason I'm doing this particular case study is it's actually for a confidential project, but it shows very nicely how Pdisp, for example, compares to FE and finite element analysis, and how the results compare. So for this particular problem, Arup was responsible for designing a building in London directly above an LUL tunnel, or two tunnels here. So an LSDyna or 3D FE check was used to model the building of the piles, but a Category 2 check was necessary. And this had to be undertaken using separate software, and Oasys Pdisp was chosen for this particular scenario. So if you look at the Pdisp analysis, you can see here that here is the displacement line, and it shows the displacement along that line. For different loadings, it also shows the displacement along the surface grid as well. So if we look at stresses here, Pdisp gave a maximum stress of 68 kPa, and so did LSDyna, so that's very comforting. And the actual pattern of stress change along the center line of the tunnels, it was actually identical to the pattern of a change along Pdisp. So this was very good verification for the program. For displacement, as opposed to stresses, the peak vertical ground movement in LSDyna was 3.18 mil, and this was compared to 6 mil in Pdisp. So in a comforting way, Pdisp was more conservative. You would expect this, and the differences occur because Pdisp doesn't model, for example, structural stiffness of the foundations, tunnels, and walls. So you would get a higher displacement with Pdisp. But also, very comfortingly for this, you could see that the pattern of displacement along the LSDyna analysis is similar to the pattern of displacement along the Pdisp analysis. So the trends of movements in themselves are similar. So as you can see, this is a very good verification of what Pdisp does, and it's quite comforting to see. So the recent developments in Pdisp are the additions of horizontal displacements and forces. The Pdisp Xdisp connection is very important, and this is very good for major projects or big projects, in that, for example, if you put a tunnel next to an excavation, but then you knew you were loading with an embankment close by, you can actually combine the results with the two programs to get displacements from an overall 3D problem, which would be actually very time-consuming and difficult to model in FE. And also the introduction of GSA Raft. So the analysis, so that's looking at analysis of soil structure interaction of raft structures. I'll cover this very briefly in a minute or two, but there are more detailed webinars which have covered this in the past. And if you are interested, I suggest you get in touch with us, because there are a lot of examples of where Pdisp and GSA have been used together, and GSA Raft has been used. So upcoming developments. Again, I'm just going to briefly mention what's coming over the next year with Pdisp, because there are changes that are being made. We've considered putting irregular loaded areas in there. So for example, currently now you can only put a rectangular area. So if you have an irregular shaped area, you would put rectangles in for that irregular shape, or rectangles and circles in. But the developers are working over the upcoming year on allowing people to just input irregular load areas, and also multiple analysis cases. So if you have an analysis case where you've got an embankment, and then you know after time that there will be an excavation, or for example there will be some kind of demolition or unloading, then you can put multiple analysis cases in. And also, as I've covered this quite briefly, again, if you go to the product page, you can download some tutorials, have a look at the 3D graphics, viewing your data, how to input your data, pile soil interaction data for programs like GSA Raft, for example, and a general tour of Pdisp. The previous webinars are in there as well, and again, they can be watched on the YouTube channel. So now I'm coming to the end of the webinar. I'm just going to very briefly cover GSA Raft. So again, this is looking at soil movement, but now we're looking at raft structures. And GSA Raft is a non-linear soil structure interaction for piled and bearing foundations. What GSA Raft is it's a combination of GSA and Pdisp. It looks at soil structure interaction for and that's vertical for rafts and vertical and horizontal for piles. So for that reason, Minlin analysis needs to be used for piles, but the Boussinesq analysis can be used for rafts. It's an iterative process, and what it is, it uses a processor, and the iteration works in that GSA assumes a spring stiffness, and GSA analyzes to get soil pressures and displacements, and that's fed into Pdisp. So Pdisp analyzes spring forces to get soil settlements, and GSA calculates new spring stiffnesses and forces spring stiffnesses from the forces and settlements, and the settlements are fed in from Pdisp, and it repeats through. So it does this iteration, and it comes to a result. So here's a schematic view of a raft model. As you can see, the piles here are represented by nodes, and the soil is represented by nonlinear springs, as you can see. So every node on the piles are connected to 3 nonlinear springs to represent the soil nonlinear behavior. So it's quite a powerful model. It's a very powerful program. It does a very good 3D analysis. And it comes to often a very useful result. So what I'll do is I'll just go on to a quick case study. I'm just going to cover this very briefly, but a detailed case study is actually available on our website in the case study section. So as you can see, this is the Aspire Tower. This was built in Doha, and it was a centerpiece for the Asian Games. And GSA Raft was used for the analysis. It was used to look at the pile-soil interaction, and it was used to actually analyze the raft in itself and the settlements. So it was used very successfully here, and the link to it is available in the bottom corner here of the page. But you can look at that in more detail in your own time. So to summarize, I covered slope, Xdisp, and Pdisp in a little bit more detail than GSA Raft. But slope is a limit equilibrium analysis of circular and non-circular slip surfaces. Xdisp calculates the ground movement due to excavations. Pdisp calculates displacements due to the application of a pressure, either due to loading or unloading. So for these programs, I've given you an idea, a little bit of the interface and where you can go to get a little bit more information. For GSA Raft, it has some connection to Pdisp in that it uses a Pdisp GSA link, and it analyzes soil structure interaction with raft structures, such as basement slabs, for example. So I gave you a specific case study here, but a previous webinar covered this program in detail. And if you are interested, please feel free to email us with regards to any of these programs. So what next? One would be to read the help file and manuals. There are step-by-step examples as well. But if you want an introduction to these programs, you might be wanting to watch some previous webinars. Previous webinars are all available on our YouTube channel. So I've kept the link here. So that's www.youtube.com// the Oasys software. Soil movement and slope stability, for example, and soil structure interaction with GSA Raft might be 2 that you were interested in, but there are plenty more. And also support. Feel free to call us, email us, look at the online training movies, and have a look at the website's technical FAQ section, because that gives an idea of the more detailed problems that people come to us with, and detailed analysis queries, and it helps a lot of people.